Hi everybody! Today I like to share my idea about the Vedic methods for the problem of last curves. In the past, I worked a few years in the statistic processing of marketing and research data, and I am thinking how to use Vedic Maths in the algorithm. My name is Anna Gerardina Foglino. I have a degree in mathematics. I am Vedic Maths certified teacher advanced level. I am naturopath and expert in bioresonance, homeschooling teacher, goal mapping and life mapping practitioner, a technique to achieve goals with both hemispheres of the brain. My intention is to spread out Vedic Maths, develop creativity, ability and respect, and take natural care of the body. The problem. We suppose we measure some points and we want to find a curve that approximates these points. For example, we can imagine having an electrical component and measuring consumption over time. Then we obtain a function that has x variable the time, and as a variable dependent we have y. Found this cluster of points, we want to do an interpolation. We want to find a curve, and it can be a line, a polynomial, an exponential, a logarithm, and a trigonometric function, etc. This is the picture of clouds of points. For this trend of points, we can decide to use the exponential function or the linear function. Here the two sample function px equal a0 plus a1 ex, the exponential function, and as x equal a0 plus a1 x, the linear function. Here the values of the independent variable x written as a vector and the dependent variable y written as a vector. We want to find the curve corresponding to the points. The points are 1, 2, 2, 3, 3, 1, 4, 4, 5, 0, 6, 1, 7, 3. Let's try with the simplest function. The line as x equal a0 plus a1x. For the equation of a line, we need 2 points. We use the method of selected point. Looking the clouds of points, I choose 2 points. For example, the midpoint 4 as abscissa value and the average of the observations as ordered. The sum of y values are 14 that are divided by 7. That's the number of the points. So we have the point M equal 4 and 2. This is 1 point. The other point I choose is P7, 3. That is a point that belongs to the line. The line can be found by the Vedic method or solving the linear system that is obtained by replacing the points of the line. I choose, obviously, the Vedic method. The equation of the line is obtained using vertically and crosswise. We have 4 minus 7, then 2 minus 3, and then the crosswise 4 multiplied by 3 minus 2 multiplied by 7. So we obtain the solution, that is x equal 2 divided by 3 plus 1 divided by x. With the method of selected points, the solution is very quickly. The solution line as x equal 2/3 plus 1/3 x depends on the accuracy of the arbitrarily chosen points. The second method is least squares method. We draw on the graph the difference between the measured values and the theoretical values of the curve, in this case the line as x equal a0 plus a1x. To summarize, we call as xi the theoretical values belonging to the interpolating line with I from 0 to 6 and yi from I to 0 to 6, the measured values. Here a graph to explain the least squared method. Let's draw the graph of measured point. Y-axis, x-axis. For each xy can be the time I measure the value of yi. x1, x2, x3, x4, x5, x6. And I have the corresponding y1, y2, y3, y4, y5, y6. I want to find the best line as x equal a0 plus a1 x that approximate the points. The x, y are the measured points, and the points on the line as x con I equal a0 plus a1 xi are the theoretical points. And here the difference between the measured points, for example y5, and the theoretical points as the x5. Here all the difference between the points. I want to find the best line Sx equal A0 plus A1x that approximate the points. I repeat, yi are the measured points that are y1, y2, y3, y4, y5, y6, and every point on the line is expressed by s xi equal a0 plus a1xi. So on the line we have sx1, sx2, sx3, sx4, sx5, sx6. The difference between the measured points and the theoretical points are sxi minus yi. And you see this difference in yellow on the graph. To have the best line, the condition is to find the coefficients a0 and a1 that minimize the distance between the theoretical points and the measured points. That is xy minus yi squared. As I have 6 points, this means to minimize the sum of the squares of each difference. I use the squares to avoid the negative values. I want to find the line as x such that the distance between the theoretical points and the measured points is minimal. Such the distance can be both positive and negative, we make the squares of the distance minimal. This means minimize the sum of square of each difference that is a function in the unknowns a0 and a1. The function is limited only inferiorly. So find the minimum means to set equal to 0 the partial derivatives respect a0 and a1. We derive respect a0. If we have a function, for example, fx equal x squared, the derivative function is equal to x. And so here we have the solution. We find the first equation, that is the sum of the 7a0, the a1 multiplied by the sum of the xi equal the sum of the yi, the measured point. That means 7a0 plus 28a1 equal 14. Deriving respect the unknown a1, we find the second equation. The second equation is 28a0 plus 140 ny equal 54. We have to solve these two simultaneous equations. we divide the first by 7 and the second one by 2. And we obtain the final simultaneous equation to solve. Using the Vedic method of simultaneous equations, vertically and crosswise, we find the coefficients a0 and a1. a0 is equal 16 up 7, a1 is equal minus 1 up 14. Substituting in the equations, we find the line Sx equal 16 up 7 minus 1 up 14x. Let's remember the solution of simultaneous equation. This method is by Bharat-Krishna. We have ax plus by equal p, cx plus dy equal q. The variables are 2 and are x and y. To find the solution, we have to find the numerators and the denominators of the fractions that express x and y. We use vertically and crosswise, using the coefficients of the equation. The denominator is the same both for x and y. We have BC minus AD. The numerator of x is BQ minus PD. The numerator of y is PC minus AQ, as you see in the picture. Another type of function. We want to use the linear combination of exponential functions. And we have, for example, this function. To find the 7 unknown e0 until a6, we have to set equal 0 the partial derivative between the theoretical points and measured points. We want to minimize this function. Here, the 7 derivatives respect the unknown a0, a1, a2, a3, a4, a5, and 6 that we put equal 0. We find 7 equations in the 7 unknown AE. The simultaneous equation can be solved using the vertical and crosswise applying a Paravayatya rule and to cycle the method. So we use the method we saw before, and then we go on in iterative manner. We find A0 and A1. We continue apply vertically and crosswise, and we find A2 and A3. If, for example, we have this type of 7 equation in 7 unknown, after do all the calculation, we try to find the solution. First, we find A0 and E1 from vertically and crosswise. Then we substitute in this A0 and A1 in the other 5 equations. And then we go on. And we can find these 7 results. There are several methods and algorithms used in calculation of the simultaneous equation, for example, Cholesky, QR, SVD. I think that vertically and crosswise and Paravayatya rule could be greatly reduce the calculation time. References. Thank you for the attention to everybody.